Hello everyone and welcome back to the Shure Masterclass Wireless Best Practices and Techniques. Today it's one of my favorite sessions. We will be discussing about frequency coordination basics. So we won't go in details about tips and tricks and how to do complicated things, but we will focus mostly on why we need to coordinate frequencies, what we want to achieve, and what we want to avoid. Sorry. Before we jump into it, a little bit of housekeeping as usual. First of all, you are all muted, but you can still interact two ways. Three ways, actually. First one is the chat, where you can say whatever you like. Then there is a Q&A section that I ask you please to use for Q&A. And the third way is answering our polls. We will be asking some questions, and then you can answer them. And we may use these polls as a subject for discussions and to understand better what is your experience and what is your need in terms of RF coordination. Sorry guys, here in Dubai it's beautiful 45 plus degrees, so AC is running very hard and I'm coughing a lot. So
Andrea, before you start,
yes, please.
We have the first poll as an introduction to this session that is live right now.
Okay, so if you go to the if they go to the right side of the screen, there is a section that should be on with a question. For professional wireless systems, every channel must operate on a unique frequency, true or false? That's a very good one. So we start really from the basics, and we will move on. So please answer our poll and make us happy. So, introduction to frequency coordination. Why do we need to coordinate the frequencies, and what do we need to coordinate? What do we have to bear in mind when we do so, and what is the ultimate goal? So, from the bottom up, first of all is we need to use unique frequencies. So every device needs to be on a specific and unique frequency. We need to do so considering the total wireless needs. So it's very important for us that we know whatever is going to happen RF-wise before, during, and immediately after our show, because this will allow us not only to have a clean and well done show, but as well not to disturb our neighbors if we have any. As we discussed in one of the first episodes, we need to remember that we are using the RF spectrum on a secondary user base, meaning that we can use whatever is available as long as we don't create interference to primary users. Most of the times, in a great part of the world, the primary user is the TV band. And primary users are TV broadcasters. They broadcast at much higher power than we do. So it's extremely unlikely that we can create interference to them. But there are situations where we may be secondary users when primary users are other wireless systems users. Whenever the frequencies are licensed, If we are talking about UAE, it comes to my mind the Abu Dhabi Grand Prix or some events in Abu Dhabi Stadium. There were primary users who got frequencies allocated from regulation authorities, and then there were secondary users who could use spectrum, the remaining spectrum. So this is very important that we know the full picture as much as possible. And then we need to coordinate frequencies. We can select frequencies kind of randomly, and maybe they work. This can happen, especially if we don't have many channels. But frequency coordination is based on some little mathematics, and calculations can be provided by the computers to make sure that our systems are not interfering with each other, so that our in-ear monitors are not disturbing our microphones, and that our microphones are not disturbing each other. So there is a little to know and some mathematics to be done before we can coordinate frequencies. Very basically, what is frequency coordination? Frequency coordination is the selection of frequencies for all our devices for an event, an installation, or whatever it is, where we want to avoid outside interference and system-to-system interference. To prevent outside interference, we need to know what other players are around, and then to prevent system-to-system interference, we need to have some mathematics and some coordination done. Before we go more into details to frequency coordination, I'd like to give you a definition of operating range. What is the operating range of a wireless device? It's the distance between a receiver and the first point where it starts dropping out. Is this in my experience at Shure, I've been asked many times, okay, what is the operating range of this type of wireless system? I do not have an answer usually. I can state, okay, under ideal conditions, or we tested it goes up to a certain amount of meters. But I do not have a clear answer. How big is the operating range of X in digital? The true answer is I don't know, because it depends by the noise floor. So here we can see 3 carriers on 3 different frequencies, 540, 550, and 560 megahertz, and that are having a different level of noise floor. Clearly, the lower the noise floor, the bigger the operating range. At the end, RF is all about signal-to-noise ratio. So if I have a good signal-to-noise ratio, my system will have an extended operating range, while if I select frequency that is already noisy, like this 550 megahertz, my operating range will shrink. So a system that can operate 150 meters will then operate only 75. But if I'm so unlucky that I selected the 560 in the example, my operating range will be extremely short. So we do not have to forget that RF noise, the bigger part of the equation, and it plays a big role in our frequency coordination. Another thing that is often misunderstood is the propagation loss. So how the distance is affecting the reception of the different signals. So the loss, it's not as bad as it can be in the audio. And under ideal condition, you can see in the graphic on your screen that between 50 and 150 meters, we really don't lose much energy. So if we start with a clean RF environment and we have a good a good environment without obstacles and without many other things obstructing our signal, we can cover really big distances. But as soon as we have an obstacle in between, as soon as we have noise floor, this propagation loss will change. Here you have five different colors, 5 different lines, and they are changing depending on how clean is the path between transmitter and receiver. So the black one on top is completely in free space. That is usually what we call ideal conditions. When the more obstacles we have, the more down we go in the graphic, and the more challenging will be to cover big distances. As we said, RF noise floor is a very big part of our equation when we do coordination, and it's usually the starting point. How do we come to know what is the noise floor of different frequencies? With a site survey and with an analysis of a spectrum. So to analyze the spectrum, we may have different devices that operate in different ways, but ultimately we need to know what's going on in the spectrum. As I said, there are different devices that can do it. The easier that comes to my mind is a Shure network receiver with an Ethernet port at the back. You will be able to connect the receiver to the wireless workbench, to our software, and you can read a portion of the spectrum. There are many other ways, and we will discuss them a little more in details later. What we are looking for during a site survey is, number one, is there any TV channel or any permanent source of interference in the spectrum that we are planning to use? Second question, are there other users in the environment that we are going to use? So who else is using RF systems? If we go to have an event in an hotel room, in an hotel ballroom, we may have someone next door. We may have wireless in use for other purposes, such as even sometimes a restaurant may have a wireless microphone to call, okay, table 6, you can see it, or whatever it is. So we need to be aware of what's around us. To achieve it, what we need to do is not only a scan that lasts few seconds, so we do not have to take only a picture of a RF environment, but we should try to look into it for as much time as we can in order to achieve solid reading and to make sure that nothing is appearing and disappearing, but we know whoever is there. What else can create interferences? Wireless systems, and it's a pretty long list. We said TV, we may have other wireless microphones or in-ear monitors. We may have intercom systems. We may have mobile phone data services if we are using frequencies that are typically not allowed, because we are not allowed to share the spectrum with mobile phone data systems. Studio transmitters link, and out-of-band transmitters. In example, we may have public safety. We may have, if you go to US, every city has a dedicated TV channels to public safety. Here in UAE, we don't have this thing as a dedicated channel, but we may have walkie-talkies and other type of radios that can use the same spectrum we use. And then we have digital equipment. We have devices like computers, CD player, DSPs of different type, light controllers, dimmers, high power, distribution box. All these things can create interference or can create problems whenever they are in very close to a receiver or to antennas. But we have a source of interferences that is usually pretty big and pretty disturbing, that are LED walls. LED walls nowadays can be the first and the major cause of noise, of RF noise in one environment. There is another problem with LED screens, that they are very difficult to predict and to read. So we'll see later on. We'll see some scans taken from LED screens, and we will identify some critical issues that LEDs are representing. TV channels. For who's living in UAE, this is not a problem, but outside UAE, this can be a big thing. So usually a broadcaster or a TV station has a repeater that can cover up to 50, 60 miles, that is about 120 kilometers. And we have different channels in different cities, so in different locations. So if I go to Lagos, in example, I have a scenario, but if I go in the same country to a different city, I see something completely different. There are some databases about TV channels, but unluckily, no database is available for Middle East and Africa, or at least there is something about South Africa, but as South Africa is moving to digital TV, it's not really reliable anymore. But first of all, we need to identify if we have active TV channels where we want to use our wireless systems. Here, I'd like to, of course, we can use, if we have a database available, we can use it. But as I said, no database is available for Middle East. So what do we do in Middle East and Africa? We need to read the spectrum. We have different categories of scanners. And Marwan, if you want, I think this is a very good moment for our poll about it. We have different categories of scanning methods. One is the network to receiver connected to a software, most likely wireless workbench. If we are working with another brand of microphones, we can still do two things. We can use a different software, or we can convert the data taken from any manufacturer. We can convert it in a format that can be used in wireless workbench. Then we may have some handheld spectrum analyzer that, again, are not immediately compatible with all the softwares, but there are a lot of conversion tools around that can be used nowadays. So if my case, I have a TTI, great handheld, small, compact, with a screen that is really small and tiny, and with a software that I don't really like much. So how I use the TTI, I set it up in a specific way to export scans on a format that can be compatible with wireless workbench. But sometimes, for whatever reason, I may be in a hurry and I don't have time to go through the setting of a device. But that doesn't matter. I can still save in the native TTI format and then convert again later on and import in wireless workbench. Or if you are lucky enough, you may have a real-time spectrum analyzer such as the Anritsu, Rohde & Schwarz devices, the big boys that you see one of them on the screen. These big boys have a big problem. They cost a fortune, and most of the time we cannot justify the cost of a $20,000 spectrum analyzer for a wireless microphone system. But sometimes they come very handy. If you have a chance to see pictures of the Olympic ceremonies, this is the type of analyzer that they use. They have a billion function. We don't really use many of them, but they are very fast, very precise, and they are capable of reading wideband in a very short time. So they are probably the best tool around. They would be the best tool, but there is something that makes XC600 my preferred tool whenever it comes to survey and spectrum analysis. Not only because it's Shure, but also because it's easy to use. Much more easy to use than in a Ritsu or a Rode-Schwarz spectrum analyzer, because it's a spectrum analyzer with similar capability, but it's built for the needs of RF coordinators, audio people, and for the needs of our industry. The Spectrum Manager can do some other things, but I'm not gonna spend time on them now. What can do as an analyzer is wideband analysis from 470 to 960 megahertz, so almost everything we may need to use in terms of frequency coordination for show, event, and professional wireless in general. And we can capture multiple scan. We can have a single sweep or continuous sweep. So we can have even up to 24, 48 hours scanning in order to have a more solid reading of what we need to know about the spectrum. These are the best tools you may have, but there are a lot of tools that can be helpful. So let's start again from the bottom. The first thing is automatic frequency scan that doesn't even require software or interpretation. If we have, let's say, only ULXD, I think the screen is a ULXD screen. If we have ULXD only, even a bunch of them, we can easily set an automatic frequency scan. The receiver will scan the full band, will find frequencies that are available, and will deploy frequencies directly to the other receivers without you being involved too much. So this, if you have only one system, your life can be extremely easy nowadays, much easier than it was 10, 15 years ago. You can do almost everything automatically. But unluckily, this is not helpful anymore if you need to combine different models. But the automatic frequency scan can still be used as part of the bigger picture. When we use a scanner instead of just a receiver, we can see the landscape and we can avoid multiple sources of interferences. Here we have some more options. I didn't mention before, I mentioned the TTI that I have, I mentioned the Spectrum Manager, I mentioned the Shure receivers. There are at least a couple more that it's worth mentioning. One is WinRadio, that is a company, I don't know if it's been bought or just there is something that relates WinRadio to Kaltman Creation, or Kaltman Creation built the modified version of a WinRadio scanner. Very popular. It works really nicely, very easy to use. It has a dedicated software that is fully compatible with Wireless Workbench. Until Wireless Workbench, when we had Wireless Workbench 5, it was actually possible to directly connect WinRadio to WWB. And luckily now it's not possible anymore because they speak, let's say, different languages. And the entry level is the RF Explorer. I'd like to spend a couple of words about RF Explorer. It's a very common and entry level scanner. Amazing value for the money it costs, but it has some limitations. And if you happen to have one of them, and if you use one of them, it's good to know what the limitation can be. The limitation is related to the internal noise floor of the analyzer itself. So if you have a noise floor level that is related to the spectrum analyzer that is about, let's say, -70, -75 dBm, you may not see many of the things that are happening around you. You'll just see, the green line here on the screen is representing a reading made with a high noise floor spectrum analyzer like RF Explorer. Other devices can have a much lower noise floor, self-created noise floor, so they can give you much more room to understand what's going on. Here you see the difference between an RF Explorer and a Spectrum Manager. Of course, this is coming with a cost, and many freelancers may say, okay, but I heard this question many times. Yeah, I cannot afford for my job a Spectrum Manager, so I'm happy when I find one, but I cannot buy one. I can afford an RF Explorer. Does it make sense to buy one? The answer is absolutely so. Yes, it makes sense. There is much difference between being blind and not being able to see everything. Okay, so a small reader is better than no reader at all. Now I want to show you some slides where we are talking about noise floor to help you identify how to read the scan. This is a kind of clean noise floor. How do we know it? We have a red line that is the default exclusion threshold set in wireless workbench at -85 dBm. All the frequencies below, with an energy that is below -85, are considered good enough to be used. As you can see, even though everything having an energy below -85 can be used, it's not all the same. In some areas, we can see in the lower UHF around between 470 and 530, I think, 550, we can see that there is much more noise than, let's say, over 600 megahertz. So the operational range will be different if we tune a microphone around 510, 515, or 605, 610. So we will have a different operating range, but both frequencies are considered good enough to be operated by wireless workbench. For who's interested in more details about wireless workbench, we've been running in the beginning of this very strange period. I think it was 6 episodes, so 6 small webinars about wireless workbench that are going pretty much in detail. I'm not going in detail about wireless workbench today, but if you want to know more, you can tune on YouTube Shure Mia channel. There are 6 webinars that you can look at, and of course, as always, you can ask questions and interact with us with a form that you receive together with a confirmation email about your registration. Okay, let me just drink a little water. And here I am again. So this is a clean noise floor, different levels of energy, but overall, I'd say very quiet. And we see only one spike, one carrier. Most likely this is a microphone or an ear monitor broadcasting already. And this is a noisy RF area. So in this picture, we can see different players, and we can recognize different things that may look familiar to who's doing RF coordination often. So to describe RF noise, we have 2 common terms. One is electromagnetic interference, or MEI, and the second one that is kind of random broadband RF noise. And then we have radio frequency interference that is something we can recognize, something that is generated at specific frequencies, most likely by RF transmitters. So here we have a mix of both things. So we have some EMI and some RFI. Something that is just very difficult to understand where it's coming from. Typically, it may be LED screens, computers, or other digital devices around, but it can be even some AC power equipment. So it's very difficult to understand where it's coming from, how it's produced, and it's usually showing like the part that you see in the center of a can without a specific carrier. Maybe it has some spikes, but they are not clearly recognizable. There is no pattern. This is the generic noise floor. But we can recognize much better the TV channels. TV channels are blocks of 6, 7, or 8 megahertz, depending on the region, and they are usually looking like this. And they are pretty clear. And this big green this big green blocks on your screen are telling you there is no way you operate on top of an active TV channel if it's as loud as -40, -50, but when they are smaller and they are below -85, -90, you may decide to operate on top of them. It means, again, that you will not have a perfect signal-to-noise ratio, but you may have no other choice. The important thing is to recognize the different sources of problems to know what you're dealing with. Another very common problem is related to two-way radios. Two-way radios, oh, sorry, someone is knocking at my door. Two-way radios are walkie-talkies. Technically, most of the countries shouldn't operate over 470 megahertz, but that doesn't mean that even if our carrier is below 470, doesn't mean they do not pollute our environment. They can do it, and they can be extremely unpredictable. They go on and off continuously. They can create different intermodulations. So they can create different spurious frequencies at different times. So it may not be immediately easy to recognize and to see them in first place and recognize them in second place. And we may even confuse them with some random energy that we don't know where it's coming from. But they often look like this. And to get this kind of picture, you need an analysis that takes minutes, if not hours, because they are not going on all at the same time, and mostly they are not producing always the same spurious frequency. Another source of interference that is difficult to identify is the LED wall. Here you can see an LED wall while it goes on without image on it. You can see that it's recognizable because you can see a regular pattern that is created by the different device, the different components inside the LED wall when they go on. But at the same time, this is not all you get. And to get this scan, again, you may run into issues because this is not regular in time. So to get the scan that is so precise, you need to run the scan for a very long time. When the picture is on, it's even more complicated because we have a higher noise floor and all these spikes that are moving. So to identify with precision this type of RF sources, you need a high quality analyzer, meaning you can recognize them using a continuous sweep of a spectrum manager or even a receiver. But otherwise, if you don't have time to do so, and if you are in a rush, you definitely need one of these big boxes with a big screen and a big price tag connected to them, like we said before. Okay, maybe Marwan, if you want, you can launch another poll. I'll be briefing for a second before we move on. Oh, in the meanwhile, I went on the question side. Tamir is asking, how do LED panels create RF? Very quick answer is they create frequencies because they are operating at certain frequencies. So they have inside electronic components that can create RF noise. More in details, you need to speak with an engineer. One thing that is good to know is that unluckily, most of the brands are not disclosing, are not testing their LED walls against RF emissions. So there is not much information about it, but how it's creating RF interferences. Let's say that every electronic device, every DSP, every even a CD player creates RF noise. The problem with LED walls is that they are big and there are a lot of tiles, so the overall amount of RF noise that they can create is very much significant. This is about the reading. So here is how we read our spectrum. What do we need to know on the second portion of frequency coordination? So how do we select our own frequencies? Of course, we will try to avoid noisy portion of spectrums as much as we don't want to create troubles to ourselves. The first thing is that each system must operate on a unique frequency. This is true, but even though there are some minor exceptions, if I think of an ADX2FD, an example, it's operating at actually 3 different frequencies because it's having frequency diversity, so it can broadcast on 2 different frequencies, and it has a remote control on 2.4 gigahertz, so this is the exception. But let's keep the exceptions aside. 98% of wireless microphones need to operate on a unique frequencies. And the frequencies must be apart from each other at least 0.3, 0.4 megs, or for some systems, but some other systems require 1.2, 1.5, up to 2 megahertz. This is depending on how selective is the filtering at the receiver stage. In addition to each system needing to operate on its own frequencies so cannot be too close together. If an undesired transmitter, something we don't really we've not taken in consideration, is tuned too close to an existing frequency, at the end, the result can be as bad as having 2 systems tuned on a single frequency. That means it won't work much. If you are curious and you want to see more in details how much space a system needs to operate, you can look at Kippen profile in Wireless Workbench, and you can, let's say, compare the different parameters. What do we need to be aware of? I said there is a little mathematics to be done by calculators. So let's start with it. 2 transmitter in an ideal world with a super perfect linear circuit will look on a spectrum analyzer exactly 2 carriers without anything else. And this is true even in the real world, as long as the 2 transmitters are not too close to each other. In that case, what we see is more of a second option. So we will see two carriers and some other small things going on. Digital systems are better in this regard. They are very much more linear than analog system, but they still produce some intermodulation. Eventually, we will get back to the difference between analog and digital systems. But with the spectrum analyzer, we have two transmitters, two carriers spaced. It doesn't really matter how much. I think here they are spaced a couple of megahertz apart, so perfectly fine. Every transmitter has its living space, it's okay. But as long as they get close together, the second picture is what we see. So a little more RF noise on different frequencies. And this is predictable. One other less commonly known source of interference noise can be attributed to the receiver demodulation circuitry. If you remember, we spoke about it in the last session. There is a local oscillator at the receiver, and the intermediate frequencies are generated inside the box. This can, if you remember, the intermediate frequencies are typically 10.7 megahertz. This is done to help the demodulation. The local oscillator frequency of one receiver may interfere with another receiver tuned to the same frequency of the difference between the frequency itself and the intermediate frequency. So let's say I have a receiver tuned to 600.7 megahertz. Its local oscillator will operate at 590. A second receiver tuned at 590 could experience interference from a local oscillator. How do we prevent it? There are two ways. One is, of course, calculations and avoiding this type of frequencies. Another thing is related to the design of the systems. So the better the shielding, the more unlikely is that intermodulation between receivers happens. And last but not least, we need to isolate the antennas, because the antennas are transmitting and not only receiving, even if they are connected to a receiver. So isolating the antenna means that we need to use antenna distribution system. If we have this nice forest of antennas, the intermodulation at the receiver stage is much more likely to happen. Between transmitters, so that said, this is a secondary cause of intermodulation distortion, but it's worth mentioning it because it's often not taken in consideration, and antenna distribution sometimes looks like an optional, but it's not. How do we calculate intermodulation distortion? We said these are predictable, so we can calculate them. Here you have all the possible products, intermodulation products created by two receiver, frequency 1, transmitters, sorry, frequency 1 and frequency 2. Now, all the equations in black are not really bothering us, because if I have as intermodulation products frequency 1, let's say 600, plus frequency 2, 601, my intermodulation product will happen to be in 1.2 gigahertz. So it's a different range, and it's not gonna affect me, my system. But there are some intermodulation products, especially third, fifth, and eventually seventh order, that will affect me. And I need to calculate them, or I need to get them calculated. The most common intermodulation distortion product is the one, and the strongest, the loudest intermodulation product is the one produced, is the third order produced by two transmitters next to each other. So if we have one transmitter 590 and another one at 595, we are going to have these two strong signals at 585 and at 600. That means 2 times frequency 1 minus frequency 2 and 2 times frequency 2 minus frequency 1. So these two intermodulation products will be more loud than all the others. Intermodulation may happen not only between two transmitters, but it may happen between three transmitters as well. So again, some more calculation, frequency 1 plus frequency 2 minus frequency 3, and so on and so forth. So if we calculate between three transmitters all the possible third order intermodulation products, we end up having, I think, a dozen of frequencies or so. But is already some calculation to do. The more we grow in the number of frequencies, the more the relevant intermodulation products are happening. So at some point we cannot keep on calculating. We need a software to do the job for us. The software is automatically taking care and giving us compatible frequencies to be deployed to our system. A couple of additional information about analog versus digital. So what we see here is the number of analog carriers that are intermodulating very much between themselves and creating a lot of spurious frequencies, but overall increasing the noise floor. On the right side, a little more ideally, there are digital systems. The carrier of a digital system looks slightly different, and the intermodulation product, there are intermodulation products even in the second reading, so even digital wireless microphones are producing intermodulation products, but they are not loud enough to disturb our communication most of the time. So intermodulation products between digital transmitters is not such a big thing as it was for analog transmitters, because the circuits in use are way more linear, and they can be more linear because the behavior of a digital signal is much more predictable in terms of amplitude and the different modulation schemes. That is something we already discussed. So in terms of, we already spoke about it, the advantage of digital system is that they create much less intermodulation, therefore they can be coordinated, an example, on an equidistant grid. So let's say I can put my ULXD every 350 meg, and even though we are on an equidistant grid, I won't suffer from intermodulation. I cannot do the same with my whole UHFR transmitters because they would purely create too much intermod to operate and too much noise floor. So frequency coordination obviously needs to minimize intermod effects. As I said, we may use a software to do it, and this would this would make our life much easier. But sometimes we may find ourselves not having a software or not needing a software. The easiest way that all the manufacturers provide to users is to use preset groups and channels. So every device has a list of compatible frequencies divided in groups. As I said before, they work for multiple systems as long as they are of the same type. So I have, let's say, ULXD. I can have even a lot of them, doesn't matter. I can choose a group, and assign different channels to the different receivers. As long as they are part of the same group, they will be compatible with each other. This is provided by all the manufacturers. What you cannot do, let's say that you have a ULXD and then you have some Sennheiser G300 or whatever, you cannot select group 1, channel 1, 2, 3, 4 on Shure, and then group 1, channel 1, 2, 3, 4 on Sennheiser, hoping they are compatible, because there is no guarantee. But even inside the same brand, let's say, and even inside the same type of wireless systems, there is no compatibility between different frequency bands. So if I have UHFR and in H4E and in it's called K1E something, so in different range of spectrum, I will not be able to mix and match, because the intermodulation created by a certain group is not compatible with the intermodulation created by a different group. So if all my devices are the same, I can use these preset groups. If not, there is something else that I have to do. I can calculate custom compatible frequency stats using a software. Then I have two options. One, I can create my compatible groups. Let's say I always go around with 4 ULXD and 4 PSM 1000. I can create a group inside Wireless Workbench that makes them compatible. So I calculate on Wireless Workbench. I save preset frequencies inside the devices, and I know that group 1, it will be called user group and not preset group anymore, will be compatible with everything else in my rig. Or the best thing is to use a software to calculate the frequencies that you need to calculate every time. Get in a scan and calculate a compatible frequency set, keeping the minimum channel-to-channel spacing, keeping the channel-to-intermod spacing, and avoiding interferences that can be created by digital TV or other sources of RF noise that we may find on site. So I'd say that this was a presentation, and do we have any question? Let me see. An Anonymous asked, is it true that simultaneous and multiple usage of mobile phones in a corporate event affect wireless audio signals on transceivers? If so, what do you suggest to eliminate RF interference without adjusting or turning off mobile or settings? So, this is a question that can get two answers. I'll start with the one that is more about theory. Do you know that when you are on a plane, when we were on a plane, because it doesn't happen since a while that I catch a plane, and I think it's for you somehow the same. When you are on a plane, you are asked to switch off your mobile. Now, you may argue that plane that costs millions of dollars can really have equipment so weak that suffer from interferences created by my mobile. The answer is that technically it can happen. The communication between the aircraft and the airport, it's still analog. So what's the use of multiple devices trying to connect at frequencies that are different but not so far away from the frequencies used by the aircraft can create some RF noise, making the communication between your aircraft and the airport a little less clear. This may happen. But did you ever try to keep a mobile on while you're flying? I think everybody did. Communication is still happening. It's just that what they want to achieve is to reduce the number of devices that, especially taking off and landing, are trying continuously to connect to the repeaters. So in theory, yes, a lot of mobile phones can create problems even in the UHF TV range. That is what we typically use to run wireless microphones. But this is not meaning that we have a strong interference or like disruption. This is meaning that we may find a higher noise floor, especially in the top 100 megahertz of our spectrum. And there is not much we can do about it. It's just a little more RF noise that we just have to deal with. It's unlikely that you ask a stadium full of people, oh, please, guys, switch off your mobile devices because I need to run a microphone. Plus, the amount of noise that they can create, it's still something we can deal with. So, can they disturb? Yes. But is it such a big deal? No. We can easily manage selecting the right frequencies, keeping some headroom. An example is if I have a big ramp and the singer I know sings a lot 40, 50, 60 meters away from the antennas, I want to make sure that I still have enough headroom at that point for when the audience will be inside. So during my sound check, obviously everything is fine, but I'm not just happy enough that everything is fine. I want everything to be absolutely fine and to have some headroom to play with for the moment when I will see the noise floor increasing. So all you can do is to do your homework as well as you can to prevent these things, the noise floor to disturb you. And then I read another question. When manually searching for an open frequency on the receiver without Workbench, what is the exclusion threshold used by the receiver? Good question. I do not have an answer because different models and different devices are using different exclusion thresholds, and as well because it will go, I think the exclusion threshold, it's still -85, the same one that is in a standard in wireless Workbench in most of the case if we are talking about Shure. The limit of that method is that is not looking for the best frequency available. It's verifying that the first frequency is available. So you may step into, let's say, for a device like ULXD that has a threshold of -85, I can select this frequency, the system automatically goes there, and it works, but I may have in the next frequency a lower noise floor that I will not be aware about. So the exclusion threshold most of the time, in Shure at least, is -85. That is also just before the first LEDs lights on, but the limit is that it's scanning the frequencies in order, so from the lower to the higher, and so this is fine for some cases, but it's definitely not the best way to do things, and this is another reason why you prefer to use wireless Workbench instead of having automatic selection. So I have another question. Most of our events include on average a 10x4 LED screen. What could you recommend for antenna spacing away from the stage to avoid the interference? How much distance the LED screens transmit the noise? I mean, it does not reach all the venue like the TV channels. So definitely, it's not all over the venue. a 10 by 4 LED screen, it's already pretty big one, so can create some relevant noise floor. I'm not going into antenna placement because this is the topic that will be covered exactly in 1 week from now. What I can tell you is that it depends very much on the LED screen. But in general, all the LED screens are emitting louder at the back than in the front. Sorry. Little water. So do not ever place the antennas at the back of the LED. Try always to keep them in the front. Use directivity. And we will continue discussing the topic next week when we will cover antennas and cabling. But definitely it's not covering all the venue. The problem is that usually it's covering the stage, that is the same area that you want to cover with your microphones. So yes, it's not covering all the venue, but it's still creating some issue to you. I already said that next Tuesday, we will be talking about antennas and cables. And after that session, you will be allowed, you are allowed even now, but you should be ready to take the exam on the Shure Audio Institute website. For who's willing to get some other clarification about the exam, about the Shure Audio Institute website, or even about the topics that we already covered during the training, there will be Sunday afternoon at 3 p.m. Dubai time, a Q&A session. So I will be showing how to register yourself, how to access the exam, and I will be more than happy to answer all the questions that you may have. If you have any question that you didn't ask yet, or it's about a topic that we covered maybe before, or if you already took a look at the exam structure or in any other case, please feel free to submit your questions in advance with a form that you received together with the registration email, or keep them for the moment when we will virtually meet again next Sunday, and I'll be happy to answer every question you may have. Oh, I see that in the chat, Ranjan is kind of correcting me. LED screens have highest emission to the sides, front and back, less at 45 degrees. Yes, partly, but the front and back, there is a significant difference. Then again, it depends very much on the LEDs. Transparent LEDs are more omnidirectional. The bigger tiles are emitting much more RF at the back. But this is kind of rule of thumb, because at the end you don't have a single tile emitting. You have a wall of LED screens that are making noise. In that case, maybe when all this thing will be over and we will be able to go around easily again, I may prepare some measurement to show the difference between the back and the front. That is still pretty significant. The main emission is not the LED itself, even though it's still emitting something. The main emission comes from a little box at the back of the LED tile. So I hope to get some other questions before Sunday, to see some of you for the Q&A session and the introduction to SAI website and the course structure and all the. I think we will take a look at the other trainings that are available on the SAI website, and then next Sunday there will be the last session about antennas and cabling. Thank you for joining me. Thank you for spending your time today here. And I hope to see you soon. Bye.